Welcome to Study Loop.
For this thermodynamic process, we are asked to sketch the PV diagram in the part A of the problem. So we need to understand the given values. Here we are given a cyclic process. This is a process that repeats itself. So the initial point of the whole process and the final point of the whole process is going to be the same point. Now, this process is also rectangular on a PV diagram, and we'll see this on the sketch here, because in the first part of the process the pressure is constant but the volume is changing. Then the volume is constant but only the pressure is changing, and then the pressure stays constant but the volume changes back inversely, and again the volume stays constant but the pressure changes back inversely into the starting point. And this is why it will be like a rectangle on the PV diagram. So let's start from the initial volume, which is 0.028, and this is all in meters cubed. And we also have some initial pressure here, which is 1.5, and the pressure is, we will express this pressure as to be in units of 10 to the fourth. It will be in units 10 to the fourth pascals anyway. So this will be 10 to the fourth pascals, and their common point is here. Now, only the volume changes, so the volume is expanding, and the final expansion point is here in 0.0435 meters cubed, so 0.0435 meters cubed, and this is their common point here. So the first part of the process is to go from here to here in a straight line. So this is the direction of the process. Now the volume will stay, this is also, let's say, first process. Now the volume will stay constant in the second process, but the pressure will change, and the final point is here, for example, and this is going to be 3.5 times 10 to the fourth power pascals. So the units for the pressure on these PV diagrams are 10 to the fourth pascals. So it will change from here to this common point here. This is their common point, and the change is a straight vertical line, like this. So I'll just adjust this a little bit. So this is the final point, and this is the direction of the process, like this. And this is the process too. Now the process, it will go backwards. So it will go to the point here, and it will go from this point back to this point, back on the horizontal axis, because the pressure is now staying constant. This is the third part of the process. And this is the direction of the process. And from this point here, it goes back to the initial pressure while the volume stays constant. So it will look like this. And this is the direction, and this is the number 4. This is the fourth process. This is the third process. This is the second. This is the first process. So you can see that this is a cyclic rectangle on the PV diagram. And this diagram is very important to understand what kind of the process we are dealing with. And this is important for the part B of the problem. Now, for the part B of the problem, we need to solve for the total work done. The total work will be equal to the linear combination or the sum of every work for every part of the cyclic process. So this is corresponding to the first part, this is corresponding to the second part, this is corresponding to the third part, and this work is finally corresponding to the fourth part. Notice that there is no volume change in the second and in the fourth process. And this means that their work will be equal to 0, both of them. So we will only have the work 1 and the work for the third part. So work for 1, since also from the PV diagram we see this is the under constant pressure, we can only take into account the change of the volumes. So we can calculate it very straightforward. It will be only P1 and then the difference in the volumes, which is equal to 1.5 times, this is 1.5 times 10 to the 5th power pascals times 0.0435 meters cubed minus 0.028 meters cubed. When we value this in using a calculator, we obtain this is equal to 233.0 joules. Now for the third part of the process, the work done is the pressure P2, since in the third part the pressure was already increased by the second part of the process, and the volume is V2 minus V1. But also notice that if we write this like this, we need to add negative sign here, because actually the volume is now going from larger volume to lesser volume, to smaller volume. So it will be a negative work and a negative value, since the gas is compressing itself back into initial state. And then we can substitute that this is equal to 3.5 times 10 to the 4th. And also one correction here, this is calculated as 10 to the 4th power. So 10 to the 4th pascals times 0.028 meters cubed minus 0.0435 meters cubed. When we put these values in the calculator, we obtain that this work is equal to minus 543 joules. And therefore the total work will be equal to, now we only need to add these values. So it will be 233 joules minus 543 joules. And the final value is therefore V total equals minus 310 joules. This is the final value for the work done in this cyclic process. And we see that the total value of the work done is negative, therefore the work is being done on the gas in this thermodynamic process. For the part C of the problem, we need to find the heat balance. Is heat getting out of the system, or is it getting in the system, inside in the system? This can be evaluated from and expressed from the first law of thermodynamics, like Q equals delta U plus W. Notice one thing, delta U always equals 0 if the starting and the end point of the whole process is the same point. Since this is a cyclic process, it is going back into the same point after the fourth part of the process, and therefore the internal change of energy is zero. So any change that happens during the process is being lost later in the process, and the process goes back to zero in the terms of internal energy change. So we only have the work W. Therefore, the total change in heat is negative, and it's negative 310 joules. And this is also expected because the work is negative as well, and it is being done on the gas. So the work is being done on the gas, and therefore the heat is being liberated from the gas system. And this is the end of this problem. The problem is solved. I hope you find this helpful, and I hope to see you in another lesson.